Much of today's video starts out as an analog signal. So, a working knowledge of analog standards and formats is essential for understanding digital video and digitization. The fundamental topics which are necessary for understanding analog video are 1. Broadcast standard. Second, video signal standards. Third, video storage formats. Fourth, digitizing video. And fifth is digitizing audio. In this video, we are going to study about digitizing video. Digitizing video involves taking an analog video signal and converting it to a digital video stream using a video capture board, as shown in the figure. Today, a variety of computer platforms including PC, Macintosh and Unix workstation offer video capture capabilities. In some cases, though, the capture equipment is a third-party add-on. The analog video source can be stored in any video storage format, or it can be a live video feed from a camera. The source can be connected to the video capture card using any three connector types. They are component, S-video or composite, depending on the connector type that the card supports. When capturing and digitizing video, the components which are critical are 1. Resolution. The horizontal and vertical dimensions of the video session. A full screen video session is typically 640 by 480, that is 640 horizontal pixels by 480 vertical pixels. Full screen video uses these dimensions because it yields the 4:3 aspect ratio of standard television. Of the 525 vertical scan lines in the NTSC standard, 483 lines are used to display video. The other lines are used for signaling and are referred to as the vertical blanking interval. Because the NTSC standard uses 483 vertical lines, capturing at 640 by 480 means that 3 lines are dropped during the digitization process. Second, color depth. The number of bits that are used to express color. At the high end is 24-bit color, which is capable of displaying 16.7 million colors and is the aggregate of 8 bits of red, 8 bits of green and 8 bits of blue. The 8 bits are used to express color intensity from 0 to 255. Other common color depths are 16-bit and 8-bit, which yield roughly 65,000 and 256 colors respectively. Third is frame rate. The number of frames that are displayed per second. To deliver NTSC quality video, 30 frames per second are displayed, whereas for PAL and CCAM displays 25 frames per second. Based on these criteria, it is a simple mathematical operation to determine how much bandwidth a particular video stream requires. For example, to deliver uncompressed NTSC quality digitized video to the network, a bandwidth of approximately 27 megabytes per second, that is Mbps, is needed. This number is derived from the calculation 640 into 480 into 3 into 30, which is equal to 27.648 Mbps or 221.184 megabits per second, that is Mbps. In this equation, 640 and 480 represent the resolution in pixels, whereas 3 represents 24-bit color, that is 3 bytes, and 30 represents the number of frames per second. As this calculation indicates, full motion, full color digital video requires considerably more bandwidth than today's typical packet-based network can support. Fortunately, two techniques reduce bandwidth consumption. The techniques are: one, video capture manipulation, and second, video compression. Video capture manipulation. Manipulating video capture parameters involves changing resolution, color depth, and frame rate. To reduce bandwidth consumption, all three variables are often changed. For example, some multimedia applications capture video at 320 by 240 with 8-bit color and at a frame rate of 15 frames per second. With these parameters, bandwidth requirements drop to 9.216 Mbps. Although this level of bandwidth is difficult for a 10 Mbps Ethernet network to achieve, it can be provided by 16 Mbps token ring or 100 Mbps fast Ethernet and other high-speed technologies. Video compression. Video compression is a process whereby a collection of algorithms and techniques replace the original pixel-related information with more compact mathematical descriptions. Decompression is the reverse process of decoding the mathematical descriptions back to pixels for display. At its base, video compression is transparent to the end user. The true measure of a video compression scheme is how little the end user notices its presence, or how efficiently it can reduce video data rates without adversely affecting video quality. Video compression is performed using a codec, that is coder and decoder, or compressor and decompressor. The codec, which can be implemented either in software or hardware, and is responsible for taking a digital video stream and compressing it, and for receiving a pre-compressed video stream and decompressing it. Although most PC, Macintosh, and Unix video capture cards include the codec, capture and compression remains separate process. There are two types of compression techniques. One, lossless, a compression technique that creates compressed files that decompresses into exactly the same file as the original. Lossless compression is typically used for executable, that is application and data files, for which any change in digital makeup renders the file useless. In general, lossless techniques identify and utilize patterns within files to describe the content more efficiently. This works well for files with significant redundancy such as database or spreadsheet files. However, lossless compression typically yields only about 2:1 compression, which barely dents high-resolution uncompressed video files. Lossless compression is used by products such as stack and double space to transparently expand hard drive capacity, and by products like PKzip to pack more data onto floppy drives. Stack and other algorithms called predictor are supported in the Cisco iOS software for data compression over analog and digital circuits. And second is Lossy. Lossy compression used primarily on still image and video image files, which creates compressed files that decompresses into images that look similar to the original but are different in digital makeup. This loss allows lossy compression to deliver from 2:1 to 300:1 compression ratio. Lossy compression cannot be used on files such as executables that, when decompressed, much match the original file. When lossy compression is used on 24-bit image, it may decompress with a few changed pixels or altered color shades that cannot be detected by the human eye. When used on video, the effect of lossy compression is further minimized because each image is displayed for only a fraction of a second, that is 15th part or 13th part of a second, and is depend on the frame rate. A wide range of lossy compression techniques is available for digital video. The simple rule applies to all of them. The higher the compression ratio, the higher the loss. As the loss increases, so does the number of artifacts. Here, an artifact is a portion of a video image for which there is little or no information. In addition to lossy compression techniques, video compression involves the use of two other compression techniques. These techniques are: one, interframe compression and intraframe compression. Here, in interframe compression, compression between frames, which is also known as temporal compression because the compression is applied along the time dimension. And for intraframe compression, compression within individual frames, and is also known as partial compression. Some video compression algorithms use both interframe and intraframe compression. For example, Motion-Picture Experts Group, that is MPEG, uses Joint Photographic Experts Group, that is JPEG, which is an intraframe technique and a separate interframe algorithm. Motion-JPEG, that is MJPEG, uses only intraframe compression. Interframe compression. Interframe compression uses a system of key and delta frames to eliminate redundant information between frames. Key frames store an entire frame, and delta frames record only changes. Some implementations compress the keyframes and other don't. Either way, the keyframes serve as reference source for delta frames. Delta frames contain only pixels that are different from the keyframe or from the immediately preceding delta frame. During decompression, delta frames look back to their respective reference frames to fill in missing information. Different compression techniques use different sequences of key and delta frames. For example, most video for Windows codecs calculate interframe differences between sequential delta frames during compression. In this case, only the first delta frame relates to the key frame. Each subsequent delta frame relates to the immediately preceding delta frame. In other compression schemes such as MPEG, all delta frames relate to the preceding key frame. All interframe compression techniques derive their effectiveness from interframe redundancy. Low motion video sequences such as the head and shoulder of a person have a high degree of redundancy, which limits the amount of compression required to reduce the video to the target bandwidth. Until recently, interframe compression has addressed only pixel blocks that remained static between delta and the keyframe. Some new codecs increase compression by tracking moving blocks of pixels from frame to frame. This technique is called motion compensation, which is also known as dynamic carry forwards, because the data is carried forward from keyframes is dynamic. Consider a video clip in which a person is waving an arm. If only static pixels are tracked between frames, no interframe compression occurs with respect to the moving part of the person, because those parts are not located in the same pixel blocks in both frames. If the codec can track the motion of the arm, the delta frame description tells the decompressor to look for particular moving parts in other pixel blocks, essentially tracking the moving part as it moves from one pixel block to another. Although dynamic carry forwards are helpful, they cannot always be implemented. In many cases, the capture board cannot scale resolution and frame rate, digitize, and hunt for dynamic carry forwards at the same time. Dynamic carry forwards typically mark the dividing line between hardware and software codecs. Hardware codecs, as the name implies, are usually add-on boards that provide additional hardware compression and decompression operations. The benefit of hardware codecs is that they do not place any additional burden on the host CPU in order to execute video compression and decompression. Whereas software codecs rely on the host CPU and require no additional hardware. The benefit of software codecs is that they are typically cheaper and easier to install. Because they rely on a host's CPU to perform compression and decompression, software codecs are often limited in their capability to use techniques such as advanced tracking schemes. Here I wish to stop for first part of this video, and due to time limitation and other reasons I have divided this video digitization of video into two parts. The remaining part is continued in part 2 of this video.